Let's work through some examples solving trig equations that involve just linear terms of our trig functions, sine, cosine, and tangent. And let's just remember the basic idea here is that we want to use algebraic techniques like factoring and combining like terms to isolate the trig term, the trig function, and then we can use the unit circle to find the angle for the corresponding coordinate, and then that will give us the solution on the 0 to 2 pi interval. And then we can express that there are infinitely many solutions as we go around the circle by adding a plus 2 pi k for sine and cosine, or by adding a plus pi k for tangent. So let's just work through a few examples here. Our first one is that we have 10 times the sine of x is equal to 5 square root of 2. And so there's not a lot of algebra that we need to do here to isolate the sine. We just need to divide both sides by 10. And when we do divide on the left side by 10, they will cancel out. And so we're left with the sine of x is equal to 5 root 2 over 10. And that may not look like a unit circle value right now, but if we simplify that right side a little bit, it will look more familiar. So we have the sine of x is equal to the square root of 2 over 2. And so that should be, we should recognize that as one of our nice unit circle values. And so we want to figure out what angle makes sine equal to a square root of 2 over 2. And so first thing to think about is that we know sine is positive in the first and the second quadrants. Okay, and we know that the point where the y coordinate is root 2 over 2 is at the 45-degree coordinates locations in each quadrant. And we want to do this in radians though. So we know in the first quadrant, the y coordinate will be root 2 over 2 at pi over 4. And then the corresponding location in the second quadrant would be 3 pi over 4. So sine of x is equal to root 2 over 2. We could say that x then has to equal pi over 4 or 3 pi over 4. Okay, so those are the two solutions on the 0 to 2 pi interval. Now, if we wanted to list out what the infinitely many solutions look like, then we need to take each of those and add in a plus 2 pi k. So I could also say x is equal to pi over 4 plus 2 pi k, or x is equal to 3 pi over 4 plus 2 pi k. And so that expresses the infinitely many solutions. That tells me what all solutions look like. Okay, so they're all going to be coterminal with pi over 4 or 3 pi over 4 as we rotate around the unit circle forever, both in the positive and negative direction. And so we'll always have those coterminal values. All right, let's try the next one. We have 3 plus cosine x is equal to 2. So in this case, to isolate the cosine of x, we just need to subtract a 3 from both sides. And so that will leave us with cosine of x is equal to a negative 1. So now, again, we want to shift gears a little bit and think about our unit circle. Where is cosine negative? Well, since cosine represents an x coordinate on the unit circle, we're going to be somewhere in the second or third quadrants. But because it's negative 1, that was one of our quadrantal angles, right? That was where we had the point negative 1, 0 on the negative x-axis. So that's where we see the x coordinate being a negative 1. And that's actually at a 100-degree angle, or again, we'll think in terms of radians. So that is at pi. And so cosine of x equals negative 1 means that x has to be pi. So this time there's only one solution if we want to look on the 0 to 2 pi interval. And so again, if we want to express the infinitely many solutions, we can just take that one solution, that x equals pi, and we can add a 2 pi k to it. So x equals pi plus 2 pi k. And that'll actually result in, if we kind of think through what it looks like to keep adding 2 pi, it'll result in just a bunch, all of the odd power or multiples of pi. So 1 pi, 3 pi, 5 pi, 7 pi, and so forth. And you could also do it in the negative direction. So negative pi, negative 3 pi, and so forth. All right, let's try one more. We have 13 plus 5 times the tangent of x is equal to 8. And so this one, we'll have to do 2 steps of algebra to isolate the tangent. So the first one is we're going to want to subtract 13 from both sides. So 13 plus 5 tangent of x minus 13 is just going to leave us with a 5 tangent of x. And then 8 minus 13 is going to result in a negative 5. So 5 tangent of x is equal to negative 5. We're then going to divide both sides by 5. And so we're left with tangent of x is equal to a negative 1. So now with tangent, again, we're going to think about our unit circle. Tangent is negative in the second and fourth quadrants. It's positive in the first and the third. And tangent is, remember, the y over x coordinates. Okay, so we need to think about the coordinates on the unit circle where the x and the y coordinates were the same. Just one is opposite, or just an opposite sign. And again, that's in the second and in the fourth quadrant. And they have the same coordinates at the pi over 4 angles. So in the third quadrant, we're going to see 3 pi over 4. And in the fourth quadrant, we're going to have 7 pi over 4. So the solution between 0 and 2 pi for the tangent of x equals negative 1, we're going to have x is equal to 3 pi over 4, or we're going to have 7 pi over 4. And again, that is just the solution on the 0 to 2 pi interval. Those are the specific ones just in that one revolution of the unit circle. So if we wanted to express the infinitely many, remember tangent's a little different. With sine and cosine, right? When we look at our sine and cosine graphs, sine goes from 0 to 2 pi. Cosine also goes from 0 to 2 pi. But if you remember tangent was a little different. Our default or standard period for tangent was from negative pi over 2 to positive pi over 2. Right? Our graph looked kind of like that. And so this has a length of just pi. So our period here, when we talked about our graph, our period for tangent was pi, whereas the period for sine and cosine was 2 pi. So instead of adding a 2 pi k, if we have a tangent equation, then I'm going to add pi k. And the nice thing here, though, is the 3 pi over 4, if I add pi to 3 pi over 4, I will actually get that 7 pi angle. And this pretty much always happens with tangent. When you look at the two solutions on the unit circle, they're always going to be a distance of pi away from each other. If I took 7 pi over 4 and I added a pi to it, I'm actually going to end up at 11 pi over 4, but that's coterminal to 3 pi over 4. So we're always going to get the same coterminal angles. So with tangent, if I'm going to express the infinitely many solutions, I don't need to use both of these. I just need to use one of them. Usually we can pick the smallest one and then just add pi k. So I could say, instead of using 3 pi over 4 and 7 pi over 4, I could just say x is equal to 3 pi over 4 plus pi k. Okay, and that will give me the infinitely many solutions. If you don't remember that with tangent, you still can express that using the 2 pi k. You just then have to use both of them. So we could instead say that x is equal to 3 pi over 4 plus 2 pi k. And then you'd also have to do 7 pi over 4 plus 2 pi k. But usually we're going to try and do it as simplified, as succinct as an expression as possible. And again, for tangent, we can do that with just using the plus pi k.